Okay, one last question was there. A project, can two people be a project group? The answer is yes. Two people can be a project group. Simple. That was an easy question. So now, let's open a new page and continue our discussion regarding convolution. You must have seen a lot of convolution videos and examples from the book, from various web pages, from YouTube videos, etc. I was trying to give you a few links for the essential material. They can be PDF material or video material on our teaching system, Canvas system by Mergen. So you must already know, but there are a few very obvious convolutions. And those convolutions are, let me turn on the pen. Those things are convolution. Let's say that this is an example. Convolutions of two rectangular shapes at the same length, at the same duration of t. For example, this is x1 of t, and the same thing, or maybe a scaled version of it. Or let's say that this is a, it's not 1, and this is b, a different scale with the same duration, and this is x2 of t on the time axis. So y of t is equal to x1 of t convolution x2 of t. What does it look like? If there are two rectangular boxes like this one with different shifts, they may one of them may be centered around 0, the other one may start from 0, or the other one may start from minus capital T and go up to 0, etc. It all determines where the convolution will start and where it will end. Let's consider this kind of a, but the shape will be the same shape, just shifted. We will flip around one of them. Let's fold around the x2 of t, the second signal, and slide it on the first one. When you start sliding the folded version of this one, the folded version will look like this, right? This is the folded version of x2 of t. If you go further to the left, of course, there will be no overlap, no intersection of the signals. As you start from here, they will start touching one another, and that touching portions will be multiplied. You have to obtain a multiplication of these. And the multiplication of two flat regions, as you move to the right-hand side, it will be, again, rectangles. The rectangle height will be a times b, right? So the multiplications will be something like this. This is the shift amount. You shift to the right by t, and the height will be a times b, okay? And as t goes further to the right-hand side, the rectangle will be larger and larger, as long as, of course, you don't go beyond this capital T. So as long as you go up to capital T, it will be, if you go there, it will be the largest rectangle, the multiplication overlapping rectangle, which is a times b times capital T. It reaches to that. So, and it starts from 0. As this capital T it was 0, it was no intersection, so it was starting from 0. Let me try to plot this y of t already on the t-axis. As you start from 0 and you go up to capital T, you will reach to this value. And it will be a linear increase because a times b times t is linearly increasing with time. And it reaches to this point, which is a times b times capital T. And what happens afterwards? after you pass capital T, this time it will behave like this. It will be smaller. Here, this is T, and this is T minus capital T, this point, and this point is capital T. And now we are dealing with some smaller areas. And as this T point here, as it increases up to capital T, this rectangle will be narrower and narrower and narrower, and it will shrink down to 0 when you reach this T to be 2 capital T. Okay, so when you reach the 2 capital T, it will linearly decrease back. So this triangular shape that we have is the typical shape that you obtain when you convolve two rectangular boxes with the same time duration, with the same width. If you have two boxes, two same width boxes, their convolution will first increase and then decrease. That's a triangular shape that you will obtain. If one of the boxes is shorter in time duration than the other one, like one of them is, let's say, capital T1, up to capital T1, and the other one is up to capital T2, where due to the shape, it seems like T2 is less than T1. And this is B. This is X1 of T. This is X2 of T. What does the convolution look like? Again, let's fold around this X2 of T, and let's have this rectangle. This is minus capital T2. Now I will try to apply the lasso tool so that I can, but it was a bit too early, so I have to draw, no. I have to draw this downgoing box too. Then I will use the lasso tool to select this box. Now, as you see, as I move this box to the right-hand side, it will overlap more with the top X1, more and more and more and more. And here it will have some maximum overlap, right, at this point. So the output will reach to a maximum, because if I move further to the right-hand side, up to here, up to the right hand, the right edge touches the T1 point, up till there, it will stay the same, because the areas of the multiplications of these two signals will be precisely the same. And then afterwards, it will start decreasing again further. Decrease, 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 decrease. And when I come to this, the left edge touches the, when it touches the T1 point, then it goes down to 0, and afterwards everything is 0, it stays 0. Okay, so this will be the behavior, and let's now try to draw that behavior of y of t. It will start increasing from 0, and as time goes to T2, it reaches to a flat plateau. And what's the value of that? It's A times B times T2, because the width of the overlap will be T2. It will not be larger than the smaller rectangular width. And up to T, not T2, but up to T1, it will stay constant. And after T1, it will go down with the same rate as the increase. which is t1 plus t2. So the rectangle convolution with a rectangle may also provide you with an increase, a flat plateau, and then a decrease. That is also a possibility if the widths of these two shapes are not the same. Now I will open a new page to give a few further examples of convolution. And one example that I will try to make is this triangle minus capital T to T. This is x1 of t. And the other signal that I will convolve is x2. And I'm going to, and this point is, let's say, A, the peak point is A. x2 of t is 2 summation. Now I'm not drawing anything. K from, no, it's not summation. I will do something else. It is 2 times delta t minus capital T plus 3 times delta t plus capital T. This. I didn't draw it, but I could draw it. What does it look like? It's essentially some shape like it's at minus capital T, the value is 3, an impulse with a magnitude of 3 at minus capital T, and at plus capital T, an impulse with magnitude 2. This is what it is. This is x2 of t at the right-hand side. 2 impulses. Now, these 2 impulses are convolving x1 of t. So what am I going to do? It doesn't really look like flipping around and sliding, because if you flip around an impulse and slide over the other one, it's like an impulse moving inside or outside the shape. If it is outside the shape, of course, we have nothing. But if it is inside the shape, what the hell is going on? It's not a regular shape. How can we multiply them, and how can we find the area underneath? The area under the impulse is 1. If it is 3 times impulse, the area under it is 3. Okay, 3 times 1. But it's difficult to think of it like that. So forget it. You shouldn't solve this problem by flipping around and sliding. If you are convolving with an impulse or with impulses, you have to be quicker than trying to flip around and slide. It's simple. In fact, convolution with an impulse is the simplest thing, because if you convolve with delta t, it means you're not convolving with anything. It's just the convolving with an impulse. You are convolving the impulse response with an impulse, which will give you the impulse response. So you get the same thing when you convolve with an impulse. So convolution with an impulse does not change the shape. It may shift the position of the shape. And how much shift does it apply? It applies this much shift or this much shift, depending on which impulse you're convolving with. And you can convolve with these 2 impulses separately and then combine the outputs. And then you have to just apply the scale of the impulse. So what does that mean? Let's start by convolving with this circled, red circled impulse. When you convolve x1 of t with that impulse only, it means that it's applying a shift of minus t. It moves minus t amount to the left, and it is scaled by 3. So the result will be, let me draw it by red. It starts from minus 2t, because originally it was starting from minus t. So you shift to the left by t, And the center point is not at 0, it's at minus t. Everything is shifted to the left. So now we have a different triangle. But it's the same shape, as you see. It's the same triangle. The last, so, and this peak value is 3a. It was originally a because the magnitude of the impulse is 3. Now it becomes 3a. Simple. You just move the shape according to the position of the impulse and scale according to the magnitude of the impulse. How about the other one? This one, the blue encircled one. Let's draw it with blue. As you see, the shift is to the right-hand side this time by an amount of capital T, and it is scaled by 2. So the center will be at capital T, not at 0. I'm convolving the black x1 of t. And it will end at 2t, not t. And the scale will be like this. This is 2a. And the overall result that we have as y of t is this. Y of t is these two triangles. You can draw it by a black pencil if you wish. So as you see, convolving with an impulse is easy. It's the easiest. The other ones are more difficult because over there you have to think of areas, multiplication areas. But here you don't do anything like that. You just move the signal and scale. I will do 2 more examples regarding this one before I finish with the examples. By the way, this convolution with impulses thing is also valid for discrete time impulses too. If there's an isolated discrete time impulse somewhere, or if there's only 1 point or 2 points that are separated from one another, and you are trying to convolve with another discrete time shape, you just move that discrete time shape to the position of the first impulse and to the position of the second impulse, and then you combine. So convolution with an impulse is easy. Just move the shape to the position of the impulse. The other example, again, I will use the same x1 of t from minus capital T to capital T. But this time, I'm going to convolve with x2 of t, which is delta t plus delta t minus capital T. These two. So the impulses are at 0, a unit impulse at 0, and another unit impulse at capital T. These two. So I will do the same. I will move this shape of x1 of t to the position of the first impulse. Let me encircle it with red, and I will obtain this same shape because it's an impulse in the center, so there's no shift, and its magnitude is 1, so there's no scale. You exactly get the same triangle. Sorry. You get the same triangle from minus capital T to capital T. It's the same. And then you convolve with the second impulse, whose magnitude is again 1, but this time it is shifted by an amount of capital T. So this capital T is the 0 point of the previous black triangle. So the peak will be at capital T, and it will start from 0, and it will go up to capital T, like this, okay? So the red and the blue triangles must be added. And when you add them, you have to be just careful about the overlapping regions, because the overlapping regions must be added. You cannot just draw 2 triangles within one another. You have to add them up. And the summation of these will give you an interesting shape. This part will be exactly like this. And in between, from 0 to capital T, the blue line is a straight going up line, and the red line is going straight down with the same peaks. So it will start from this peak and it will end at this peak. And in between, it will be a straight line, which means it stays flat because the angles are just the opposite of one another. So the summation will be just the same constant, and it will go down. So the situation will be from minus t to 0 to capital T to 2 capital T, something like this, a trapezoid shape. As you see, sometimes convolution with impulses may cause overlaps. Okay, so you have to be careful about that. The left-hand shape doesn't have to be a triangle. It can be a box shape. So you are convolving, which means you are reproducing different rectangular shapes, and they overlap. When two rectangles overlap, in the overlapping region, it makes a taller rectangle as opposed to the non-overlapping places. And another example is you may have a rectangle like this from 0 to capital T1, and the other is x1 of t. In x2 of t, you may have another rectangle from minus capital T2 to T2, and at with a value b, and an impulse at capital T3 whose magnitude is c. So how are you, I'm not going to do this. I'm just going to tell you how to approach such convolutions. The way to do it is you first get rid of, or don't think, ignore the impulse and convolve the two rectangles. How do you do that? You fold around one of them and slide over the other one. You have to go to the left as much as possible so that they start touching one another. They start overlapping, and slide as long as they overlap. And afterwards, or before touching, they are all zeros. So you draw the convolution of the two regular shapes first. And then you convolve x1 of t with the impulse in the red circle. That impulse convolution with x1 of t will give you the same x1 of t shape, scaled and shifted by t3. So you will have an isolated rectangle box starting from t3 and going up to t3 plus t1, right? That will be the convolution. And you had a previous convolution too. Draw them isolatedly and add them up. The summation signal will correspond to convolution of x2, because x2 of 3 is equal to like z1 of t plus z2 of t. z1 of t is the rectangle box, z2 of t is the impulse, and x1 of t convolution with z1 of t plus z2 of t is equal to x1 of t convolution z1 of t, which is the convolution of the two rectangular or regular shapes, plus x1 of t convolution with z2 of t, which is convolution with an impulse, or there may be even more than one impulse. So depending on the number of the impulses, you one by one implement them. And if there is another shape, you just implement that convolution with that regular shape, like this rectangle, separately. You just separately try to convolve. Okay, that's how you do it. And before the break, the last thing that I want to give you as a hint. I like convolving a signal with a so-called impulse train. Impulse train. And it has a way to write. It is x of t is equal to a, that's the scale of the individual impulses. And this is a periodic signal with infinitely many impulses. K from minus infinity to infinity. It may be a finite train too. Then K would start from some integer index, and end at another integer index, but it may be infinite impulse train. Delta, in parentheses, T minus K times capital T. Now, this is a very typical way of writing something as a combination of infinitely many impulses. What is this separation of each individual impulse? For example, for k is equal to 0, delta t minus k times capital T will be delta t, which will be this impulse, right? How about the others? When k is 1, for example, delta t minus capital T. That's an impulse at capital T. All the values are a, it's the same. When k is equal to 2, it will be at 2t. When k is equal to 3, it will be at 3t. When k is equal to minus 1, it will be at minus t, right? So it goes on like this. It's like a comb that you, when you comb your hair. It's called an impulse train. And convolution of anything with an impulse train makes infinitely many replicas of that shape just around these impulses. Because when you convolve, for example, this one with this impulse, it will make this rectangular box. When you convolve it with this impulse, it will make this rectangular box. When you convolve it with this impulse, it will make this rectangle. When you convolve with this impulse, it will make this rectangle, etc. So it will make a train of boxes. It will be like this if capital T1 is less than capital T, right? Because then the box will fit inside one period of capital T. It will be smaller. But sometimes this capital T1 may be larger than capital T. Then, of course, it will still be an infinite replicas, but there will be overlaps everywhere. So how do these shapes look like? What happens if it is a sawtooth triangular shape or a symmetric triangular shape? That I may think of several such shapes to make replicas. And I may think of several widths, actual widths of those shapes, as opposed to the period that I'm using in the impulse train. So what's going to happen here? This is a very typical question I just love to ask in every year's Signals and Systems midterms, okay? So if you encounter with this kind of an expression, don't be terrified, don't be confused. It is an impulse train, and it has just infinitely many or several impulses like this one. And don't be scared of convolving anything with an impulse. You just have to put a replica of the shape at the position of the impulse, as simple as that. Of course, you have to be careful with the scales. All right. Now I want to give a break, because after the break, we will continue talking about the properties of the convolution, like what other things we can talk about convolutions, what are inverse systems, so can we invert an operation of convolution and things like that. So before I stop the recording and give some break, do you have any questions? Yeah. Hocam, 3. hafta videosunu paylaşacak mısınız? Yes, I will share, of course, the 3rd week's video. as soon as I find the time to upload, because I'm very busy with dealing with preparing notes and the department chair businesses and other projects and things like that. So whenever I find the time, of course, I'll do that. Okay, there was a private message regarding the project, but Mehmet Uluf Çerçer, regarding your project topic, I approve, and it's simple. That means it's not very complicated, and it's just the correct project title. You can do that, and that would be a very good thing. But you're saying that we are going to do it with Arduino. Now, indicating that you do it with the hardware, or indicating the hardware of that's irrelevant to our discussion of signal processing. Of course, you have to do it with something. You can do it with Raspberry or Arduino, or with a computer programming language like Java or Python, or whatever you may do. Of course, you have to do it, but you don't. That's not the title for us. It's because this is not a digital project, digital electronics project. So you have to focus a little bit to the concepts of signals and systems. How do you find the frequency of something, taking Fourier transforms and things like that? Those implementations, I care more about them. But if it runs actually on a physical perspective, really runs on a digital system, then it would be excellent, of course. That would be preferable. So the answer to your question is yes, that's a very good
Teşekkürler hocam.
But I didn't tell the other guys the project because maybe they didn't want me to. So sorry about that. Now I'm just stopping the recording, and we will meet at 10 o'clock sharp. Okay? Until then, take care. At 10, we will meet again.